Lecture 31 begins with a review of the imaginary part of the K equivalent that we have seen we can obtain through the spectral analysis tool that we have developed. And as an example, we cite the Adams scheme, which shows the asymmetry in terms of instability near the inflow, and this can be at times cured by introducing what is called as a buffer domain technique which is used near the outflow, and the compact scheme interestingly enough actually mimics this buffer domain technique, because it has tremendously high dissipation near the outflow boundary. So, if we are talking about a propagation problem, the waves will propagate through the domain, and when it will come near the outflow boundary, it will be attenuated, and that will save lots of problem of wave reflection from the boundary, which seems to be a major problem of computing. So, this is what we would be talking about. We also would highlight that the very often used outflow boundary condition as a fully developed boundary condition is not always adequate, because it can lead to some kind of wave reflection, and if we have developed a method which is stable for a wave that is propagating from left to right, then this reflected wave will be unstable with respect to that algorithm. So, this is a major issue that we will have to be working on, and then we will again switch back to the optimization method of Harasan-Tesson in developing a scheme for a periodic problem. And once we adopt this optimum scheme of Harasan-Tesson and add Adams boundary closure to it, we notice again that the instability problem is retained. So, this actually tells us that we need to do somewhat better, and we talk about truncation error minimization as optimization problem by taking care of boundary closure properly. And we note that we use the Fourier transform technique, and this relates to its property with respect to the impulse response, and we will revisit this optimization problem with respect to white noise excitation only, because any other estimates will be a less conservative estimate. So, white noise excitation gives us the outer bound. Having defined the mean square error through this norm, we can actually develop an example. That is what we will be doing, introducing the optimization problem as a 2 parameter problem, which will be actually using the grid search technique in identifying the optimum values of these 2 parameters. This will basically conclude our discussion on developing optimum scheme for compact scheme methodologies. And having done that, we also would highlight another source of error which is not covered in the above, that is namely the aliasing error. This happens whenever we do include product evaluation either in the transform plane as a linear equation or nonlinear equation. So, this is something that we will be talking about, and we will introduce aliasing as such. I think we were discussing yesterday about what is the role of the imaginary part of this K equivalent that we have here in this equation 22. You can see that while calculating the spatial derivative in an exact form, what you do, you multiply by I k, right, and numerically that this I k is represented by I k equivalent. Okay. If I have this I k equivalent split into the real and imaginary part, the imaginary part goes on the right hand side, right. You look at the corresponding dissipative equation. Okay. So, this is the source of dissipation here, and when I write in the Fourier spectral form, then I will get del u del t plus c this is equal to minus nu into this will give me k square, right. So, what happens is you can see this term appears here with a negative sign, right. So, that is what you have to look for when you obtain k equivalent by k and plot it versus k h. You look at the imaginary path, wherever you have negative sign, that would give you a dissipative effect. If k imaginary is negative, that is the dissipative effect. If k imaginary is positive, then what we said yesterday would be that you would have a anti-diffusive effect, right. So, that is what we did talk about, let us say this scheme here. In this scheme, what you see here, that for the point 1, point 2 and point 4, that you see the imaginary part of k equivalent, all these 3 points you are seeing here, it is positive. So, in a numerical exercise, these 3 points, well, actually it would show all the way up to the 6th point. If you see, the 6th point is marginally unstable, it is slightly positive on top. So, all these first 6 points, you would see numerical instability. In the same way, if you look at on the other side of the domain, j equal to 30, you have a massive dissipation. You can see these values, and this is j equal to 29, and you can see j equal to 27. So, what happens is, near the inflow, if I am solving this problem in a domain like this, let us call this j equal to 1, and this is at j equal to 30. So, what we are seeing up to the first 6 points, we are getting numerical instability. And this, on the other side of the domain, you would get to see very high damping, right. So, this is what I thought I will explain to you clearly, because I think after the class we had a discussion, and I thought everybody would benefit if we. So, you can see the role of the imaginary path, that is very interesting, and this sort of portrait was obtained only when we could basically do a full domain analysis. If I do a local analysis, I would not be able to do it. In fact, all the way up to 2003, many people have come out with local analysis, and none of them could actually get a portrait of this kind, and this was shown in 2003 for the first time with that matrix stability analysis that we talked about in last couple of lectures. We could study the full domain in one go, and the reason that we have chosen this model equation is pretty much obvious, because we are trying to take a model equation which is really non-dissipative or non-dispersive. So, if you are trying to test out your scheme numerical method, nothing can be better than this. This provides a very critical test on your ability to look at the dissipation and dispersion of numerical schemes. Okay. So, I suppose this is what we did talk about. Here we have talked about the dissipative property of the Adam scheme, and what we notice that it becomes more dissipative as you move towards the outer part of the domain. And interestingly enough, this could be very beneficially used in practical computing, and let us see how it is done through an example. What we are seeing here is called a receptivity of a flow over a flat plate. What essentially one does here is excite the flow at a fixed amplitude and a fixed frequency, and the flow is computed in the domain guided by this inflow as well as the outflow here. And what happens during the evolution of the flow is nothing but the growth of periodic disturbances that actually grow in space. Now, if you excite the flow here, these are essentially unstable waves, physically unstable waves. That means the amplitude keeps growing as you go downstream. And if you are talking about computing such a flow, of course, one cannot take an infinite domain, because eventually this instability will lead this laminar flow into a turbulent state, and even there we would not be able to know what precisely the condition would be at the end of the domain, what we have called here as the outflow. What we notice that this practicality of computing, which leads to truncating the domain to a finite size, forces us to consider the inflow and outflow. Inflow, the conditions are unambiguous, but at the outflow we do not know a priori what the solution would be. And this is a rather interesting aspect of computing as compared to theoretical aspect of solving a problem, because in theoretical problem we always consider the flow in an infinite domain, and we expect the disturbances to decay far away from it. And in contrast, in computing we are always forced to take a finite domain, and as I mentioned, outflow is a major issue. Now, because this disturbance is growing downstream, if we abruptly end the domain here and try to forcibly give some condition at the outflow, that can lead to either a spurious reflection of this wave or an attenuation of this wave. If we could attenuate this wave, that would be perfectly fine. Then we could disregard a part of the flow where it has rapidly attenuated and retain the rest of the flow, and that is precisely what one would like to do in an ideal situation. Now, if you look at various packages available, what one does usually is called as a fully developed condition, and in this fully developed condition what we do is we take the physical variable and we enforce its streamwise derivative equal to 0. Unfortunately, this does not tackle a problem where we are talking about this kind of wavy nature. That is where we need to adopt what is called as Sommerfeld boundary condition. If the wave is reflected back, then you can see what will happen now. If you look at your previous portrait here, what we told here that these are dissipative points, right, j equal to 30 and 29, but this is dissipative with respect to a signal that is propagating in the downstream direction. Now, suppose I get a reflected wave, what will happen? It will be it will have numerical instability. So, you can understand that in actual real life computation, it is so much important for you to appreciate the role of the numerical methods vis-a-vis what you are actually computing. Suppose you are solving laminar flow or say fully developed turbulent flow, it is not so difficult. Okay. When you try to study subtle physical flow, subtle physical effects like how disturbances grow and give you an unstable scenario, physically these are physical instabilities, right. These are not numerical instabilities that we are talking about. We are talking about capturing physical instabilities. Those are crucial tests, and if you do that, and if you are not very sure what you are going to do with this, you are going to get into serious problem. Actually, you will not be able to do anything. Now, what do you do? What people do, and people have found out that you can create a layer of the flow field, introduce a buffer domain. So, what we are actually doing in the buffer domain, whatever these disturbances are coming in here will not allow it to grow. If we have the numerical overstability like this, serious damping that we have here, so what will happen in this path? Instead of this wave actually growing, numerically will attenuate it. And if we do so much that when we come to the end of the domain, the wave has artificially been damped out. So, there is no question of its reflection back inside again in the domain.
So, this is the role that buffer domain plays in actual computations. Wherever you have information propagating via waves, you may be better off artificially constructing the buffer domain, like what we have shown in the blackboard. But this portrait tells you very clearly that this particular method or methods which actually display this kind of property near the outflow behaves like a buffer layer for you, because in the outflow path of the domain, any disturbances those are coming there, they will be severely attenuated and you will not have this problem. And this is what we just said in the second. The amount of dissipation added for this outflow points are quite large, and this will work like a buffer layer used in many flow transition problems. So, I explained to you what this flow transition problem is, and you can appreciate the utility of such a layer that basically will decay perturbations to 0 at the outflow. So, have any spurious reflection from the outflow boundary. This is a major benefit that you can derive from the property of this method. Okay. Now, I think we can go back to where we were yesterday, and we were looking at various schemes, and what we were looking at how to improve the accuracy of the scheme, and I briefly mentioned about these two scientists' work on developing new schemes which had this following property. It had very high spectral accuracy, and you can do it very easily. So, the computational speed is quite fast. However, you must notice that they also solved the same problem, the 1D wave problem, 1D convection problem. And then what they did, they started off from that equation that we wrote. This this is the stencil with which we actually start working, and then because they were looking at a periodic problem, periodic 1D problem, then all you need to do is tweak this to get you the accurate solution. So, this is applicable at all points, periodic problem, right. So, we do not have to worry about near boundary closure, and all these issues have been sidestepped by considering the periodic problem. Now, what you do actually is try to minimize the error that is created by this compact scheme with respect to a spectral method over the full range, and then you can see that departure is going to be a function of these three parameters alpha, a, and b. And we have already noted that what we need to do is we need to ensure this consistency condition to be satisfied exactly. So, this is what we wanted. So, essentially then this objective function that you are setting up as the departure of the compact scheme from the spectral method, there you have to satisfy this equation, and from that objective function you can derive two more equations to solve these three unknowns, right. And they did that, and they found that these values of alpha, a, and b are this given by equation this relation 34, and you can see that this is what we are anticipating, that you do not have those fancy numbers, rational quotient like I by j kind of thing. What you get is truly real number, and these are very nice spectral property of the scheme, and you can ensure by looking at that this is valid, that 1 plus 2 alpha would be equal to a plus b. Okay. And we noted that this has a much better property than the 6th order scheme. Now, what has happened in this optimization issue? We have only satisfied the equality of u prime, right. So, what is the order of the scheme? Order of the scheme is, well, it is second order scheme. So, even within the compact scheme, earlier we showed that compact schemes are much superior than the explicit scheme. Now, within the family of the compact scheme, what we are noticing here, that if you do a careful optimization, then you are going to get a much better resolution of this second order scheme as compared to the sixth order scheme proposed by Adams, right. So, this was quite interesting, and if we now do one thing, that we try to investigate how this scheme will function. Suppose if I want to solve a non-periodic problem, right. So, if I want to do the non-periodic problem, what I could do, I could borrow those boundary closures that has been given by Adams scheme, and we have already noted they are fourth order accurate schemes. So, as far as that order accuracy is concerned, it is not going to go any inferior, because your basic interior stencil is second order, but you are giving fourth order boundary closure for j equal to 1 and 2 and n minus 1 and n. And then what happens is you get this picture. Now, this may look slightly better than the Adams scheme, but it's still, you can notice for j equal to 1, j equal to 2, and all the way up to j equal to 6, you are going numerical instability, because the imaginary part is positive for this first 6 points. So, what happens is Harasan-Tassan scheme was an eye opener, in a sense that it does open up possibilities of developing schemes with very high resolution. Why do we say high resolution? Now, you see Adams scheme, we had k equivalent by k, the real part was close to 1 up to 1.5, and after that it started falling off. But you notice here, for the interior stencils, the middle of the domain, if you leave out the boundary points, then it remains flat all the way up to about 2.2, 2.3. So, maximum you can go up to pi, and this scheme actually helps you go all the way up to of the theoretical limit, right. So, this was a good thing, but still we notice that despite its excellent spectral resolution, imaginary part actually shows a large instability for those inflow part of the domain, and we do get intermediate wave numbers where you have large instabilities and milder instabilities at extreme wave number for j equal to 2, and for j equal to 5, this instability property actually starts coming down. Okay. But that leads us to making a confession that you are still not ready to use it for practical application, because the numerical instabilities are there. However, this analysis tells us the efficiency of the optimization process, and we could perhaps exploit it, and that is what we can do. Okay. What we would do is, let us say that we are trying to find out the first derivative via optimization process. So, what we could do is we could obtain the exact representation of the first derivative as L of kh, and the corresponding discrete representation is LH of kh. Then we can find out this L2 norm that we have been talking about. So, basically what we are doing, we are finding out the mean square departure of the error, and this is obtained at let us say at the jth node. So, this is a local property. So, what we could do is we could sum such departure across all the nodes in a domain, and we can construct a global objective function, which is sum of all this, and this is what it would look like. Okay. Now, what happened in Harasan-Tassan's exercise, they were solving this problem with periodic boundary conditions. So, they took some initial conditions, and those initial conditions were kind of restrictive, in a sense they are band limited. What one could perhaps do is make that restriction also disappear. So, what you do is you take u of k as equal to 1. What does u of k equal to 1 mean? I think this is something also I wanted to discuss with you, because I noticed that not all of you are familiar with the property of Fourier transform. So, if I just briefly state that if I have a function here, like this, then of course I can plot its Fourier transform, and I would perhaps see if it's a Gaussian, then it will also be a kind of a Gaussian. Okay, this is a very nice, well behaved function. The Gaussian functions form a member of Hermitian functions. They have this unique property that the original and its transform has identical appearance. However, if I take a function like this, a periodic function, what do I get? So, what would be its transform here? Its transform would be given by the wave number, right? And what it would be? It would be a delta function. So, if this corresponds to k naught,
then the spike in spectral plane is also at k naught.
Okay. That if in the physical plane the function is all pervading, it goes from minus infinity to plus infinity, in the k plane it is very localized, it is present only in one point. Now, if I look at the other extreme, that in the physical space I have a delta function, right. So, if I have a delta function, let us say at x equal to x naught, what will I get here? You will get what is called as a white noise. You will get this f of k is equal to 1 everywhere. That means what? All the wave numbers are equally excited. Now, you will understand that in all those high school experiments, when you started doing all those vibration of a pendulum, what did you do? You always gave a impulsive excitation, right? You took the pendulum in one point and then let it go. So, that was like this, an impulse that is imparted into the system. The moment you impart an impulse, what it does, it excites all the wave numbers and frequency in the system, so that you are not doing any discrimination. So, what will happen? Your input to the system is equally spread over all wave numbers, all frequencies, and then what the system does, system actually picks up the natural frequency and displays it. That is what you see, the pendulum eventually settles down to its natural frequency. So, you have already done it. So, what you are seeing that if you have a very localized disturbance, that is going to be a very, very tough case for you to consider, because now you can see all k's are excited. And so, when we are also going to do this optimization business exercise, what we are going to do is instead of u of k square, we just simply put it equal to 1. So, what we are doing, we are not discriminating like Haras and Tassan. Haras and Tassan may have done something like this, a band limited thing. So, what happens, that becomes, that optimization becomes somewhat like a problem dependent exercise, it is restrictive. So, we wanted to restrict that, and we did that, and that is what you see in equation 36. We have put u of k equal to 1, so that we can talk about the toughest possible problem that you can have. Okay. Now, okay, so this is what I have been talking about. So, this is what is explained. Now, what you notice here, L of k, if I am obtaining the first derivative, what is L of k going to be? It is operating on u, right. So, this actually give me in k space as IKU, right. That is our theoretical estimate of the derivative. So, for each k, all I need to do is take the transform multiply by I k, and that is what we are going to substitute in equation 37 here, L of kh. I will just simply write it as I of k. Now, what about this the discrete operation? If you recall, yesterday we wrote it as I k equivalent u, right? And this we wrote it as that is your I k equivalent, and then you multiply it. And this itself P L j we wrote it as the real part, the imaginary part, like this. Okay. So, that is this part times E of k. So, this is how we write in equation 37 the expression for the theoretical estimate of the derivative, and this is the corresponding numerical estimate of the derivative, and you substitute that and work out the details. So, this is how it would look like, right? CJL into RLJ, and the imaginary part will be I times CJL ILJ minus KH, and this is the this is a complex number. So, you take its multiplied by conjugate, you get a squared quantity, and that is what is going to be your local optimization function G of j. Well, there is a bit of algebra involved. You can go through it, and what you find that everything depends on what now? Your numerical method that fixes the C matrix, and once you have the C matrix, this is what your optimization function is going to look like. Okay. So, it involves, if you are looking at the jth node, it involves some constant part that of course comes from this part L of kh part that gives rise to this first two terms, and the rest of the term comes from this numerical approximation of the derivative, and it comes out in the following three groups the way we have written down. Once corresponds to the node itself, so Cjj square, and then we have this type of product term which involves interaction of the neighbors of the jth, because you see we are restricting it to L not equal to j. So, it is summed over L equal to 1 to n, excluding j n equal to j is written out here separately. Okay. In addition, we have this kind of term where Cjl is divided by L minus j. So, now if you are focusing on the jth point, you notice that if Cjls are non-zero, they are going to be affected by all the neighbors, right. So, this is what we get. Now, you can actually use this representation or this formulae for any particular method you choose, provided you know the corresponding C matrix. Okay. So, that is the clue. Now, we have also noted that in general for a general discrete scheme, C is essentially equal to A inverse B. However, if you look at explicit scheme, A matrix is the identity matrix. So, C is equal to B, and you also notice that the thing is error. So, this Gj is some kind of an error. So, Gj actually scales with n. More you have, larger the number of points, the error will be more. So, it is somewhat little counterintuitive, because we are given to believe that we refine the grade more and more, error will come down. But you are noticing that n comes here as a scaling parameter. So, actually Gj is directly proportional to n. So, n increases, the error also would increase. That is that. And you also notice one that this is a square term, right. So, this you cannot minimize, you know, you cannot choose any particular Cjj for which your Gj can be reduced, except the condition that you choose the Cjj itself as 0, right. So, if Cjj's are 0, if I construct the C matrix and if I maneuver to get Cjj equal to 0, then that would be a good thing to happen, because that will minimize Gj. This one is also a quadratic set of term, and this will also not going to help you much, because that we have neighboring points on either side, they come in a antisymmetric form. So, this is also a square set of forms. So, this will not be able to get you any way by which you can minimize G of j. The only thing that will allow you to minimize Gj is this term, okay? This second term, that would be what you can actually do. Okay, so that's the nature of the term that you are seeing. Okay, and you can also very clearly now see that the way this neighbors of jth point contribute. The next point would be j plus 1. So, L minus j would be. So, that quantity would be what? Depending on L minus j is plus 1 or minus 1, you are going to get a minus 1 sign. So, the next points on either side of the jth node, they actually reduce, and the very next point again you are going to see that this will become positive. So, we will have to probe a little closer and see what we get. Okay. The first and foremost is you can see that if this quantity is going to be minimized, it would be in our interest to keep the scheme as compact as possible, because more number of Cj's are involved, Cjls are involved, they can give you a constructive as well as destructive interference. So, we do not want it. So, in a better way it should be that that the immediate neighboring points produce the maximum effect, because it is divided by L minus j, right. So, if I look at the second point, it will be half L minus j equal to 1 is the, it is going to give you the most contribution. L minus j equal to 2, it will reduce the contribution of Cj, and so on and so forth. So, that is what we note here, that this should keep our scheme as compact as possible, because then we would be able to minimize that. So, if you now look at those set of terms, look at the contribution coming from L equal to j plus 1 and j minus 1, that is this contribution given here, 4 times CLL minus 1 minus CLL plus 1. So, thus to minimize Gj, we must have this point to the right should be positive, and the point to the right should be much greater than point to the left, or the point to the left must itself be negative. Okay. So, what happens is to not compact scheme, but the explicit scheme, C itself is B matrix, right. So, the B matrix are chosen by us. So, we can see what happens, and you notice that inspecting the B matrix itself, we can talk about least error schemes, and we have already noted that we want to do something, the diagonal term should be equal to 0, and that is what you get in all central scheme, right. If I look at the jth node, I always put that coefficient equal to 0. So, that is something that will tell you why central schemes are preferred. Central schemes inherently gives you Cjj equal to 0. Whereas, if you now look at say second order central difference scheme, so Cjj is 0, and these are what you get, Cj j plus 1 is plus half, and Cj j minus 1 is minus half, and you can work out that expression, and this is what you are going to get for the second order central scheme. Now, if you look at the corresponding fourth order central difference scheme, you notice that Cjj is once again 0, and then next neighbors are 2/3, and the subsequent neighbors give you a contribution of which is 1 by 12. And you can see now, look at the expression given in 42 and 43, and you can very clearly note that a fourth order scheme is a better scheme than this as a quantitative estimate, because there we are subtracting 3.5, you are subtracting 4.76. So, of course, fourth order scheme is better from this analysis point of view also. Okay. Now, if we now come to optimizing a compact scheme for first derivative, we can actually follow the route which Lele had taken earlier, and what he did was, of course, tried to obtain a fourth order internal stencil. So, that is the stencil given here in 46 for internal points starting from j equal to 3 to j equal to n minus 2. For j equal to 2 and j equal to n minus 1, we can use that same fourth order scheme we talked about. This is a central scheme. So, this points towards the correct direction, whereas at j equal to 1, we do not know what to do. So, we write the scheme like this. So, for j equal to 1, we say the derivative at the first point is related to derivative at the second point with respect to this coefficient alpha, and on the right hand side in the function value we take 4 points, because our experience in 80s have shown that we could do a upwinding scheme for this j equal to 1 point, and that should be okay. So, basically if I look at this, I could try to get this A, B, C and D here in terms of alpha, and the same way I could get A1 and B1 in terms of alpha 1. Then what happens is my optimization function exercise would be function of alpha and alpha 1. Okay. This is what was attempted there. So, we could do that, as I said, that with the help of the stencil given at the first point and equating the Taylor series coefficients, we can work out this expression for A, B, C, D in terms of alpha like this. Okay. This gives us a third order accuracy, right? Whereas the internal stencil we can work for fourth order accuracy, and we can get A1 and B1 in terms of alpha 1. So, what happens is the global optimization requires basically looking into alpha 1 space, and which we can do it, because now we can estimate Gj at alpha and alpha 1. And one thing you notice though, if I go back here, look at this equation. This equation is written only for 1 point, whereas this equation we have written it for many points. Okay. Now, you look back to what you did in your exam or an elliptic equation. We have seen that one of the attributes that we must try to do is to keep the corresponding linear algebraic equation diagonally dominant. So, what that would do? That gives you some limit on the value of alpha 1, right? What should be that alpha 1 then? It should be less than half. If it is less than half, because you see diagonal term has a coefficient 1, so and the off diagonal terms have give you a contribution of 2 alpha 1. So, 1 plus 2 alpha 1 should be, means 1 minus 2 alpha 1 should be positive. So, alpha 1 has to be less than half, whereas this point is only applied at 1 point, and we do not perhaps need to be that fussy about the diagonal dominance, and it says that alpha should be equal to less than 1, but if we violate also that, marginally it should not cause tremendous problem. Okay, so that is what we make the point here, that alpha 1 should be less than equal to half, so that we get the corresponding A matrix as dominant, and we should be able to use Thomas algorithm without any problem. The same logic requires that alpha should be less than 1, but we can still obtain the C matrix with this condition mildly violated, and this is what we are going to show. What we are going to do is we are going to obtain this value of G that we have shown in the bottom of this slide and plot this G in alpha alpha 1 plane. So that's so basically we are showing you this error that optimization function G global optimization in alpha alpha 1 plane. What you notice is along this groove the function actually goes up. So instead of having a maximum along this line, you get this going to be very, very large. Whereas optimum value somewhere here in the middle. Okay, and this is also the region where your diagonal dominance actually breaks down. So that's estimated here also, that if you calculate, you see the corresponding errors are also going to be very large. Okay. Now, so having obtained this value of alpha and alpha 1, we have for the whole domain with non-periodic boundary conditions. How does it function? Well, you can plot it. You can plot it the real path k equivalent by k real path in the k h or k delta x plane, and you can see various points behave like this. So this is your j equal to 1 point, and these are the other points. You see a slight overshoot here and some bit of degradation here for close to the boundary points here. So those we have shown only half the domain, so I did not show the later half of the domain. So that's what we are seeing, that this is the real path. So we do see that there is some benefit. However, if you plot the imaginary path, this is what it is, and this is not very encouraging at all, because you can see j equal to 1, you have very severe instability for any kh above 1.5, right? And if j equal to 1 is not also considered important, then you look at j equal to 2, 3, 5, etc. They are also selectively, scale selectively unstable. For j equal to 2, perhaps all wave numbers are unstable. For j equal to 3, you will see that high wave numbers are unstable, and j equal to 5, you see a very interesting thing. There is an intermediate range over which it is unstable. Then that is followed by another intermediate range where it is stable. Again, at very high wave number close to the Nyquist limit, again this is going to be unstable. Okay. So of course we should not be surprised, because we did not put any constraint on the G to avoid numerical instability, and we are paying the price here, right? So if we don't have any constraint on the G, we end up developing so-called optimum scheme, which will have numerical instability. So I suppose we now have come to realize that even when we are trying to develop compact schemes, and if we keep the stencil like what we have done here, what we have here, the basic stencil is given here, right? And they are central, right? So central schemes appears to be not holding up a lot of promise for us. So what we could do is we could look for the alternative, should be able to develop schemes for under the umbrella of compact schemes, right? So what we are going to do is basically try to develop some upwind scheme. However, we need to really talk about another source of error, which we have kind of avoided talking about so far. We don't think we can postpone it any longer, and that source of error is what is called as aliasing errors. Now, this is something I need to spend some time. Now, notice that as compared to this convection equation, if I try to solve it in a grid which is non-uniform. So, basically what we are talking about, that I have a domain like this. Okay. Now, say I know that initially I have structure in such a way that I need to resolve it, and I need to have, let us say, grid like this. So, we talked about it before also, that if we want to use compact scheme and in a non-uniform grid, what we should be doing? Well, we would transform the x plane into a transform plane, which I will call it xi. This I should divide it by del x del y. So, basically if that is your x plane in the xi plane, I would have uniformly spaced point, and now whatever we have developed so far, we can use them, right, because they were all developed for uniform space point. So, if we do this, what has happened now? Now, you see, this is a quantity that is a function of xi, independent variable. In addition, this transformation function that we have tried to get. So, x is a function of xi. We may actually do it analytically, we may do it numerically, but we will have to what has happened. This was a sort of a linear term, right? But what has happened now here? It has become a product of two functions, and a product of two functions dependent on xi. How do we represent it in a sense of in the K space? This is what we anticipate. Let me write for simplification of that this is f of xi, and let me call one of del x del xi, let me write it as z of xi. Okay. Now, if I am writing this, I could write it as f of k, let us say e to the power I k xi dk, right. That is the definition of Fourier transform. Let us write this as, well, dummy variable, I change it to g k prime and e to the power I k prime xi dk. Now, what we are trying to do there, we are trying to solve an equation of this kind. Right. Now, what happens? This is where we actually get into a bit of a problem now. Now, if I am trying to estimate f times g, right. So, what we are noticing, that this product, if I may call this as p of xi, I could write that product function p of xi would be some, let me call that as p of k bar. Okay. Now, what has happened here? K and k prime, what is its range of variability? The Nyquist limit that we need to do here. So, we will be writing here, say, minus k max to plus k max. So, what happens to this? This shows a variation, this phase variation is shown here as minus 2k max to plus 2k max. But given a grid, can I do that? We cannot, because our grid is capable of handling only from minus k max to plus k max. But trying to take the product, we see that we are trying to spill out of the region. What happens? I have already told you what happens in computing. Even though we are working in a limited region, we always take its periodic extension on either side, right? So if I am trying to resolve a problem from minus k max to plus k max, and in the process I spill out to say minus 2k max to plus 2k max, what happens to this region? They cannot physically stay there. Okay? At the same time, this problem is repeated, right? So what does it mean? That what we are seeing from minus km to plus km, the same thing should have happened here, minus 3 km to minus km, right? So these points are what? These points have a corresponding image inside here, because they are the periodic extension. So what happens is, this point would map first point here, that should be the first point here. So what happens to this point? This point would this point. So what has happened is, the one that is supposed to be have gone there, numerically it will be transposed to this region. The same way, this part also would map in this way. This part would. So anything that spills out, it is reassigned in a new region, new point. And this is something you must have to understand, that what is happening now is some component of the product cannot be resolved properly, and they have been given a new name. This is what we call by aliasing, right? Alias means that, you know, all those bad people, they have some nicknames which we call as X alias Y, alias Z. So this is also something happening very bad here, which should not be kept, but we are pushing them and contaminating the good region where we do not have error. So this phenomena is called aliasing error. Okay? So we'll talk about it a little more on the next class. This is a major issue and it's not very trivial. Okay? So we'll talk about it.